the engineering that went into it, what that might say about the longevity of Curiosity. Does it strengthen the chance that you'll go beyond your 2-year Earth time mission?
Well, the big difference between Curiosity and Opportunity is that Curiosity is built with internal redundancies. Most of the major systems are redundant. Opportunity is single strength. We have a single, processor. We have a single power supply. We have a single communication bus. Any of those components fail, the rover dies. The fact that the rover has lasted so long, speaks to the design and the testing of that system, and many of those same engineers designed and tested Curiosity. So that said, I think it bodes well for Curiosity, but, in this business, who can say? I mean, why did Opportunity last so much longer than her identical twin, Spirit? Spirit had problems with the mobility system after just 2 years of driving, and yet we've gone almost 10 years with Opportunity, and the mobility system is still hanging together. And these are brushed motors, and we thought these brushed motors would have given out long ago. So, this is like, your car not lasting, 200,000 miles or even 1 million miles. We're talking about a car that lasts, 2 million miles without an oil change. So, at this point, how long Opportunity lasts is anyone's guess, but I think it speaks well for Curiosity.
I can tell you that the scientists who happen to be on both missions and have experience with this long-lived Opportunity mission, they're beginning to eat right and exercise more, so they'll be around for the extended mission for Curiosity. So we expect it to go a long time.
Sounds like everybody's got good attitudes. Let's go next to a question from Emily Lakdawala of the Planetary Society. Emily?
Hi, thanks. This is for Steve or Ray. I'm trying to understand the relative timing of the formation of the Esperance vein and the crater and the Burns Formation. Could it have formed at the same time as the crater? Is this something that happened later? And I know there are gypsum veins and concretions. Just how many times has all of this rock been wet?
Yeah, that's a good question, Emily. Let me take a quick crack at that. The rocks that we see at Matijević Hill, including Esperance, we believe are older than the crater. We believe they predate the crater, and they were there when the crater formed. So there was an episode of water activity that took place in the Meridiani region before Endeavour Crater even formed, and that is recorded well in the minerals that we see, the chemistry that we see, rather, at Esperance. Then the crater formed. That's when we piled up all those impact breccias that Ray was talking about and piled those on top of the crater rim. Okay. After that, there was an episode of water activity that produced the gypsum vein that we have seen. Okay. And then there was continual water activity following that deposited all of the evaporite sediments that we see across the Meridiani region. So there is a lengthy, multi-step history of water activity at this region. The important new news here is that we have now gotten a glimpse of what we know to be the oldest of all of these episodes, and it points to a chemistry that's dramatically different from the acid chemistry that dominated later.
And the bench rocks probably represent the first sedimentary rocks that drape around the remnants of the rim, and they're cut through with gypsum veins. So to put that in the stratigraphic order also.
And if I can follow up, I'm just wondering how similar the clay mineral is that you're seeing here to what's being seen at Gill Crater, or if Opportunity can even say anything about that with its limited instrument capabilities right now.
I wouldn't want to go too far down that road. I mean, we feel very, very good that we have such compelling evidence for an aluminum-rich clay, but we're trying to draw inferences from elemental chemistry, whereas Curiosity has X-ray diffraction. So I wouldn't want to go any further down that road than I've already gone.
Thank you.
Okay, our next question is Craig Kovalt from Space Rep.
Hi, thanks everybody very much for doing this. For Steve Steve and Ray, how high up the habitability scale are you with your findings, especially there at Esperance? And if you'd had a drill and a SAM with you like Curiosity's got, would you have used it at this location?
Okay, to answer your second question first, hell yeah, absolutely.
That's what I was going to say. That's the exact words.
Yeah, I mean, no question about it. This is a treasure trove. In terms of how far up the habitability scale, this is the best that we have found with Opportunity. This is the most compelling evidence that we have found for waters with a neutral pH. So yeah, this is the best yet for this rover.
Well, a quick follow. Was this area, I should say, habitable, potentially a habitable environment?
Yeah, I think so. I mean, in the sense that the fundamental conditions that we believe to be necessary for life were met here. We've made the point earlier that even that we found what you could broadly consider to be habitable conditions in the rocks out on the Meridiani Plains. Despite the fact that they were very acid, we know that there are organisms on Earth that can survive in a very acidic environment. The tough thing about an acid environment is that it's very, very hard, we believe, to get prebiotic chemistry, the kind of chemistry that could lead to the origin of life going under low pH. The current research suggests that you need a more neutral chemistry for that. And that's what's exciting about this discovery, is that it points to a neutral pH at a time very, very early in Martian history compared to the stuff that we've looked at previously.
Thanks.
Okay, we're going to go to a question now from Space.com and Mike Wall.
Oh, yeah, hi. This is for Steve. I mean, you mentioned that this vaults into the, top 5.
That's my personal top 5, yeah.
Yeah, and I was just wondering, what are the other 4 on that list?
Oh, gee, okay. So what would be my top discoveries? Certainly the discoveries that we initially made at Eagle Crater with the sulfate-rich evaporites and the hematite blueberries and the ripples in the rock. Certainly the silica that we found over at Home Plate with Spirit that points to probably some kind of hydrothermal system there. I would say the carbonates that we found at a place called Comanche, also with Spirit. So, those, maybe it's my top 4, It's hard to put these things in context. I mean, we just found this in the last few weeks, and with the maybe in hindsight in a few years, I'll look at it differently. But it's in my top 4 or 5. Ray, what do you think?
I'd add meteorites to it. I didn't expect to be stopping.
Those were fun.
On the experiment.
Those were fun.
That would get it to 5.
Yeah.
Just a quick follow-up, too. I mean, what are some of the processes that could have actually transformed Mars from this environment where there is neutral water to something that is just covered with this acidic stuff? I mean, obviously it's just speculation, but I mean, what are some of the leading ideas for what could have caused that transformation?
Ray, you want to take that one?
Yeah, I mean, if we go early in Mars time, when there may have been what I call an open hydrologic cycle, where you had neutral groundwater, rainwater coming in, percolating in, and having more or less neutral conditions, a little bit of corrosion, a lot of transport to produce the alluvial fans, the lake beds, and all the rest. And then you move to a situation with a lot of volcanism, slightly colder conditions, groundwater still moving through, a lot of dissolved sulfur and iron, oxidizing conditions on the surface in terms of the atmosphere, for example. Then you move to a gentler kind of situation with groundwater upwelling, and you form these evaporites. But the evaporites are really acidic materials, forming in an acidic environment. So I think it's a movement from an open hydrologic cycle with neutral rainwater coming down or snow and then percolating into the subsurface, as opposed to a system that's kind of drying out, where you have a lot of groundwater moving through, but with a lot of iron and sulfur that's coming up, meeting an oxidizing atmosphere and producing these very acidic sandstones, sulfate-rich sandstones we've been seeing. And it's probably coupled to the transition from the early wet Mars to the cold, dry Mars that we have today. You know, as the volcanism was perhaps changing, as the magnetic field was perhaps decaying, as the rate of hydrologic activity and tectonic activity was kind of moving in the transition from the open system to the very dry system we have today. All the details need to be worked out, you know, but the more we look, the more it fits into this kind of broad context. If we figure this out, you know, it really is telling us a lot about comparative planetology for a period of time where the record basically is almost non-existent for the Earth.
Thank you.
Okay, our next question is Todd Halverson from Florida Today. Hey, Todd, you there? Let me one more call for Todd, and then Todd, are you there?
Yeah, can you hear me?
Yes, we can hear you now.
Okay, sorry about that. I just have one question, and I think it's for John. I was wondering if you could give us an idea of what your annual operating costs are for mission operations. I assume it's pretty much a bargain given the fact that you're already there and the rover is operating well. Thanks.
Yeah, right now we are, in gross numbers, we're spending about $14 million a year for everything.
Okay. All right. Our next question comes from Ken Kramer at Universe Today.
Hi, thank you. Thanks for taking my question. Well, one I had was just the same as Mike Wall, was what caused this change of water from neutral to acidic, but I guess you've answered most of that. So maybe you could talk about, do you plan to drive uphill at all at Solander Point? And if you could talk about a little bit of the evidence from orbit for phyllosilicates at Solander. Thank you.
Go ahead, Ray.
You want me to take that one, folks? Yeah, we can drive up rocky surfaces, maybe 10 to 12, up to 15 degrees. And one of the areas we're looking at now with the rover planners, the engineers can, is exactly how to approach Solander Point. One idea is to drive outboard toward the west, out west of the rim, drive up a little bit, then turn left, and then drive downhill over the winter so we don't have to drive up those relatively steep slopes. Because we want to go through that stratigraphic section, and we'll be on these north-facing slopes, and driving down is a lot easier than driving up, although we can drive up. We just have a lot more kind of slip and yaw of the rover. So that's kind of in discussion now. Now, the issue with regard to the phyllosilicate detection, we found it in Mathievich Hill. And in fact, once I processed the data, Steve and I said, gee, we have to turn right. So if you look at the traverse on Cape York, we were driving down the inboard side of the bench and made a right-hand turn. That's when we realized that that's where these smectites would be. The reason we could see them is we commanded CRISM, which is the hyperspectral imager on the Mars Reconnaissance Orbiter, to oversample in the along track direction. So rather than getting the pixels kind of cheek to jowl, we overlap them probably 60 to 70%. And Ken, what that allows you to do is to sharpen the image along track. And the exposure of these smectites seen from smectite, from CRISM rather, is along track. They're elongated along track. So it was a nice match for this very special observation mode called a long track oversample. We don't have that for Solander Point. So we only have these 18 meter per pixels. And with that resolution, we just can't tell if any of those outcrops that I showed in the PanCam in fact have this smectite or a montmorillonite signature. So we have to get close up and personal with opportunity to do the investigations. And using all the knowledge we have from the coordinated CRISM and opportunity observations on Mathievich Hill, we go in smarter. And we'll have a pretty good idea of what to look for.
Do you